It's my pleasure to welcome Emma Strubel to the talk today. They're an assistant professor in the Language Technologies Institute in the School of Computer Science. Emma's research lies at the intersection of natural language processing and machine learning, with an emphasis on computation and data-efficient AI approaches. Their work has been recognized with a Madrona AI Impact Award and Best Paper Awards in flagship NLP conferences. Emma was also named to Business Insider's AI Power List of 2024 as an expert and powerful influence on the social impacts of AI. Today, they'll be discussing challenges and solutions for environmentally sustainable AI.
Thank you for the lovely intro, and thank you for the extended, fantastic, sort of intro to my talk, Valerie. Like, you've made my job much easier. You've used a figure from one of my papers that I'm also using, so it's like we planned our talks together. It's fantastic. But I'm excited to talk a little bit more about, going deeper into the environmental impacts of AI models specifically. I'll talk a bit about large language models, but also sort of other AI models more generally. Yes, so I don't think I need to tell anyone in this room that climate change is an urgent and complex problem that's going to require, sort of significant cross-cutting transformations across sectors, across energy, land, infrastructure, manufacturing, of course, industrial systems, in order to limit global warming to, be as much below 1.5 to 2 degrees Celsius as possible. So that's sort of like the inflection point at which we're anticipating some catastrophic changes, to society and our lives as we know it. Yes, and so throughout my little intro slides, I'll have like a few little pictures from my life of how climate change is already impacting me. And this one is a picture of my street here in Pittsburgh, which has been collapsed for the past few years due to a sinkhole. And sinkholes and landslides are an example of how climate change, and specifically like the increase in severity and frequency of extreme weather events, is going to impact Appalachia and many other places in the world. Okay, and so my training is in natural language processing and machine learning, so I'm sort of an AI expert, but I really care about this issue. Yes, and so I've been thinking a lot about how we can use AI to, as AI as a transformative technology, and how can it, be helpful to transform, these systems that we need to transform in order to try to mitigate climate change. I don't need to talk that much about this because Valerie gave like way more detail and fantastic examples than I'm going to give in my slides. Yes, and yeah, AI does have a great potential to help in this cause. The example that I was going to give is in decarbonizing electricity, but honestly, I'm long-winded, so I won't spend the time talking about this because, again, I think Valerie gave like a bunch of fantastic examples of things that are happening right here at CMU, towards this end more generally. And then this gives me a little bit of time to talk about some of the stuff that I've been working on, which ties in fantastically with her talk. So again, I work more on like large language models. But one area that I've been working on in this space, since my PhD, is in sort of discovering and decarbonizing materials. Valerie, in your talk, you said, why am I talking so much about steel production? Well, I'm an AI person. This is supposed to be about AI. I'm an AI person, and I love telling AI people about steel production. Right? So, cement, steel, and petrochemical production sort of together make up about 25% of global greenhouse gas emissions. So if you care about this issue, you should be focused on trying to decarbonize these processes, just as Valerie discussed. And I've been doing sort of work on that in sort of, looking at how we can use large language models as sort of like research assistants to help sort of accelerate that process for scientists. And this is a cool quote that I like from a paper from a few years ago about material science specifically. It sort of points out that, some of the most exciting breakthroughs that have happened in that field were actually when, the material people were looking for, or, catalysts or whatever it was, had actually already been found, but just in a completely different area, and like the scientists, in this other field didn't know about it. And that's a fantastic application for large language models, which are just inevitably going to be much better than us humans at like reading and sifting through like an enormous literature or like multiple literatures to try to find that valuable information. And then very briefly, I think I don't consider myself techno-solutionist, so I think that technological advances are not the only piece of the puzzle and like part of the solution here. And so I do talk to policymakers and things like this, but I'm also thinking about sort of like technological things that we can do with AI to assist policymakers in developing and implementing effective policies, specifically at the sort of like local level. So I have a collaborator at UCSD who's sort of like a climate policy person, economist, and we're working with him to try to understand how we can use large language models to assist policymakers in analyzing and auditing of like local sort of municipal and county level climate action plans, which is where a lot of this sort of implementation of strategies that are going to be impactful to local communities for mitigating their local climate hazards is happening. Okay, but Valerie talked a lot about this, so now I'm going to focus on the environmental impacts of AI. So all this is fantastic. At the same time, according to folks like the International Energy Association, who put together these scenarios or pathways towards achieving these important, greenhouse gas emissions reduction targets, we actually need to reduce the greenhouse gas emissions due to data centers and data transmission by half by 2030. And as I'll show in a few minutes, we're actually sort of making negative progress towards that goal currently, likely due to AI. And I'm actually part of I'm the CMU PI on a big NSF expeditions and computing project, which is focused actually exactly on this goal. So figuring out the underlying sort of like methodological and technical approaches and algorithms to try to minimize this data center energy use. So I'm the AI lead on this project, and why do we need an AI lead on this project? So back in 2019, when we thought models were sort of first starting to get big in NLP, and starting to become concerned about the computational requirements of machine learning, I worked with some collaborators to try to actually quantify this. So we quantified some sort of common like greenhouse gas or carbon emitting processes, like air travel for one passenger round trip between New York and San Francisco, or the average American life for 1 year, and then we compared those to the environmental impacts of various training of different sort of machine learning models or natural language processing models. And so one result that I find really interesting is that the amount of sort of computational energy use that went into my developing like a model that I published in a conference in the previous year, like would have effectively sort of doubled my personal carbon footprint if I hadn't used a green supercomputing center, which I appreciate in Massachusetts. And then there's this number that was sort of resulted in these various news article headlines, which is that the amount of greenhouse gas emissions required to basically identify a machine translation model using neural architecture search, if they had used GPUs, would have had greenhouse gas emissions similar to multiple cars' entire lifetimes, including fuel. So this is actually very old now, right? This is 2019. We've done follow-up work. This is one example. So this is in collaboration with folks at Microsoft, working on the Azure cloud team. And so these are numbers from, based on the actual data centers where these actual real workloads were run. So across the x-axis here is like a bunch of different models. The biggest one here is a 6 billion parameter large language model, which is actually considered pretty small by today's standards. And this estimate is actually from only like 13% of the training process, because we didn't want to rerun it, and this was the data that we had access to. And this was in sort of 2022. And the actual greenhouse gas emissions, at this data center where they trained this model, 13% of the way, was equivalent to about the emissions from the average US home in a year due to energy use. And we are now really seeing these impacts sort of pan out. So I mentioned earlier that we're seeing sort of negative progress. So there's some news articles discussing, Google's reporting of their sort of year-over-year greenhouse gas emissions in their 2024 ESG. So they're like, corporate sort of environmental sustainability report. And they reported that since 2019, their greenhouse gas emissions have actually increased by 48%. And this is not at all unique to Google. I would bet you money that sort of any ESG that you look at from any sort of AI-first tech company is going to report something similar. So Baidu specifically calls out the rapid development of LLMs as posing severe challenges to their significant efforts to develop green data centers. And this is despite like sort of significant efforts also reported in these reports to reduce these numbers by a lot of smart people. So Baidu's reporting like a 32.6% increase over 2021 in greenhouse gas emissions. Microsoft is reporting also like an almost 30% increase over 2020. And they're blaming investing in the infrastructure needed to advance new technologies. This is basically like buying a lot of GPUs. But this is actually not a problem that is specific to large sort of corporate tech firms. So the EU also has a CHIPS Act, sort of very similar to the US CHIPS Act, with the goal of moving more like microprocessor production to their own land, place, country. But it's estimated that if they actually achieved their semiconductor production goals that they cite in the CHIPS Act, this would potentially increase emissions due to that industry by like 8 times, which would actually result in that being higher than sort of industries considered high emissions like steel and chemical production. Okay, and then in the US, we're also, we're really seeing that this is impacting our progress towards these greenhouse gas emissions targets. So this is a chart from a Wall Street Journal article from this fall. And so what we're looking at here is projections over time, so starting in 2024, looking into the future of the amount of coal energy production that is being retired. So higher is better here. Higher means like less coal production energy, which means less greenhouse gas emissions due to energy production in the US. Basically, in 2024 over 2023, this projection is much lower because we're actually seeing for the first time in, I think, decades, that like electricity demand in the US is growing after decades of being flat. And this is for a lot of reasons. It's not just because of AI and data centers, it's also because of electrification and things like this. But it is anticipated, this is a similar chart, but sort of looking at just like fossil fuel generation extensions. This is when you have to kick in like sort of like fossil fuel electricity generation when the sort of like existing maybe better sources are not sufficient for demand. And so some estimates, although I don't really believe these numbers necessarily, estimate that data centers are actually accounting for like 30% of this expected growth in energy demand. And so the reason I don't really trust these numbers is because if you look at these estimates for data center energy use, they vary quite widely. This is a collection of sort of estimates from different entities about how much electricity we anticipate data centers are going to use in the US up through the year 2030. And you'll notice there's almost a 500 terawatt hour difference across these estimates, which is a pretty significant amount. It's equivalent to about 10% of the projected US electricity use in 2028. And this uncertainty is like largely driven by AI. This is a chart from the recent report on data center energy use and performing a bunch of projections that I think are pretty high quality from Lawrence Berkeley National Lab. And this is again a projection over time into the future of data center electricity consumption broken down by like the hardware that is anticipated to be sort of driving that consumption. And the purple part here on the top, which you can see makes up sort of like the largest chunk of these things, and most of the uncertainty in these estimates is the sort of specialized AI hardware like GPUs. Okay, so yeah, so hopefully, you know, I've conveyed, or we have both conveyed, that AI has really great potential for both positive and negative impacts on the climate and energy use sort of more generally. Yeah, and so in my opinion, achieving benefits that outweigh the costs is going to require better understanding of how AI impacts the environment and how that varies as a function of its capabilities. So basically better benchmarking and measurement and you know, data definitions and reporting. And then I also think, you know, we need to be working to build sort of energy and data efficient methodologies that are you know, best focused on enabling applications to climate change. For the rest of this talk, yeah, I'll basically try to tell you a bit more about what we do know about the environmental impacts of AI and large language models. Yeah, and like a little bit about my thoughts sort of moving forward and what's needed, where the gaps are. Okay, let's skip this slide. Okay. So I'll talk a little bit in more detail now about how the different ways in which AI can impact the environment. So most of what I've talked about today and sort of most of the focus of like the research community more generally, or at least the ones that I'm involved in, sorry, are the operational impacts. And so these are the environmental impacts that arise due to the actual sort of just development and use, sort of directly from the development and use of AI models. So they also have embodied environmental impacts, and so this is due to the manufacturing of hardware, transportation of hardware, building of the actual data centers and infrastructure, and then sort of end of life and disposal of that hardware, primarily. And then, of course, AI also has downstream impacts. Those can be either positive or negative. They can be direct or indirect. And this is how the models are actually deployed into the world, right? So are you developing and deploying an AI model that's going to be used to accelerate oil and gas exploration, or is it going to be used you know, to accelerate you know, discovery of new, more efficient, cheaper photovoltaics? And so a little bit more specifically, these things arise through greenhouse gas emissions, of course. So the example I've talked about a lot is like fossil fuel-based data center energy. So water withdrawal and consumption is another way in which AI impacts the environment. And so this happens in a number of different ways. So a lot of water is withdrawn and consumed in hardware manufacturing. And it's also used, for example, in evaporative cooling in data centers or in electricity production. Waste production is another way in which AI impacts the environment through, for example, mineral extraction or in manufacturing. And all of these are sort of direct examples of direct impacts, or all the examples I've given so far, direct impacts. But there's also, and so these are the ones that, you know, arise in a sort of relatively immediate and clear way, again, from the development and use of AI. Indirect impacts are ones that we also believe to arise from AI, but the effects are mediated through these other sort of cascading variables and factors, like our economic and social systems. And so if I don't go too long and I have time, I'll talk about more details later, or more examples of this later. But one example is, for example, induction effects. And so in the case of AI, this might be where AI enables targeted advertising that leads to you know, more purchasing of like plastic things that creates sort of more waste, for example. And so here's this fantastic figure. I think you're actually using like a better, like a newer version of the figure that I should probably update my slides to use. It's probably the version that's actually in the paper. Yeah, so thank you for introducing it. Yes, so you've already introduced it. Valerie did a great job talking about sort of the middle, and so I'm going to try to talk about, sorry, like the central circle, as a reminder, yeah, what we're seeing here is these sort of different, impacts arising from AI. And as we move to the outer circles, we have both, we believe, increasing scope of impacts, so much greater positive or negative impacts, but also much greater uncertainty and difficulty in actually measuring and trying to quantify and understand those impacts, right, due to these like indirect effects, for example. But yeah, so I'm going to focus for a bit on this sort of like innermost circle, which is the easiest to understand. And we're still not doing like the best job that we could, I think, in doing that. Okay, so from the top down, what does AI energy use sort of like look like, and how does it arise? So in terms of like global greenhouse gas emissions, ICT, which is sort of all of like computing broadly, is estimated, at least as of 2022-ish, to be about 1.5% of greenhouse gas emissions. I think it's like closer to 2 now, and this corresponds to like 500 to 700 terawatt hours of electricity use in 2022. This is like, I think, growing pretty dramatically. So how much a subset of that is due to AI? Immediately already, we have like very poor estimates of what that number is. But according to a couple, reports based on sort of data center operators sort of saying things, it's maybe 10 to 30% of data center workloads are AI related currently. But you saw those sort of projections from Lawrence Berkeley National Lab that maybe it's going to grow a lot, maybe it's not. We're not entirely sure. I think it's probably going to grow a lot. Yes. Okay. And so what do these AI-related workloads look like? So I think in order to understand AI energy use, you sort of need to understand like the AI model lifecycle. And each phase of that lifecycle has a different I guess, amount of energy, but also frequency of that energy use, right? So inference is the use phase. That's when you actually sort of like query a model, run a model that exists. The amount of energy, for that inference is like relatively small, but those inferences are run very, very, very frequently. So I'll cite a tweet from the OpenAI CEO, Sam Altman, I think later in this talk. This is how we get this information, by the way. Where he cites, basically that OpenAI is processing like billions, doing billions of inferences per day, approximately, something like this. So we also have to actually create the models, and we do that with training and development. So training a model requires sort of more energy, but that's happening less often. And then sort of developing a model, which is sort of like identifying an entirely new model, which requires a lot more sort of computation to figure out what the model should look like and what the data should look like, and hyperparameters and things like this. That's going to be sort of the most rare process, happening mostly in sort of like research labs, but it's also going to use the most energy because it requires multiple training, like many training and inference loops. So we have a little bit of data that's now sort of old about this from some companies. So as of 2022 at Meta, the breakdown of their energy use used for AI looked like this. So it was already in 2022 sort of about 2/3 inference and 1/3 training and development and experimentation. It's probably going to increasingly become inference over time, and I'll talk about that in a little more detail. I think the other thing I like here that's really interesting from Meta is this sort of bar at the bottom, which is breaking down for one of their specific models. They don't say exactly which one. It's a recommender model. It's probably something like recommending ads for your Facebook news feed or something. And so for that model, they also break down where the energy use is coming from. And this yellow part is just from data. So this is something that we largely sort of like ignore, I think, at least in the like machine learning AI community. But actually almost like 1/3 of the energy use is just sort of consuming and processing data, right? Because they need to be basically updating their models sort of constantly in real time, essentially, with new data as it comes in, and that's like a huge, huge energy cost for them, computation cost. So I want to talk, a little bit more about, so all of this talks, there's many different types of AI models, right? And like a lot of the AI models that Valerie was talking about are not necessarily these large generative AI models. But it is the sort of large generative AI models that are sort of starting to take over. They have these sort of exciting capabilities, and sort of the more advanced things you want to do with AI, it certainly right now is a little bit easier to do them with these larger generative AI models. So I want to talk a little bit about why those models specifically use so much energy. And so the problem is basically that the current state of the art for advancing AI capabilities is to increase computation and energy. It's the best way we know how. So we both scale training. So we train models on as much data as possible. And this means, so in order to train on as much data as possible, we need to sort of scale the size of the model in terms of the number of parameters, proportionally. This is a chart from like the GPT-3 paper that sort of, I think does a good job demonstrating this. Don't worry too much about the x-axis. The y-axis is, accuracy. So how well are these models doing on sort of interesting tasks? And these 3 different lines correspond to 3 different model scales. And so basically you can see quite clearly, so growing in like orders of magnitude. You can see quite clearly basically that the larger model does sort of like much better than the smaller models. This is another sort of similar chart where we have like model scale in terms of sort of combined training examples and model size on the x-axis. On the y-axis is accuracy, and each little chart corresponds to a different task of interest. And so what you're seeing, they're calling this like emergence of abilities. I wouldn't call it anything like that. But what you are seeing is that there's a certain scale that's needed for these models to like sort of all of a sudden do well on these different tasks. And we just don't really have a great way of circumventing that. But so increasingly, it's like we've sort of hit diminishing returns from scaling training. And so we're now actually sort of shifting, like the models are about as big as we can make them, I guess, with the amount of data that we have from like the internet. And so now there's been a shift to instead start scaling inference. And this is actually sort of exactly the innovation that everyone was very excited about when DeepSeek came out. Because they basically figured out how to scale inference in addition to training, or instead of training, actually. Scaling inference, you have this model, it has some size, and now what you want to do is, we can't really train it necessarily to do much better, but at test time, we can sort of adapt to these sort of inevitable test time distribution shifts by using, longer prompts and these really long chains of reasoning. So essentially, the model is like just doing a lot more computation and work to try to figure out the answer at test time. And so rather than changing the size of the model, this increases the input and the output size of the model. So you have more tokens potentially going in through the prompt, and then more tokens being sort of like generated as the response. So the amount of energy required scales like linearly with this number of input and output tokens. This is a figure from some of our sort of in-submission work, on doing sort of like a deeper quantification of the energy requirements, for inference in these models. And then, so this is a plot actually from the DeepSeek report, where they're sort of bragging about what a great job they did, basically figuring out how to scale these like long inference time chain of thought reasoning chains, to very long lengths. So at the end here, the generation length is like 10,000-ish tokens, which is quite long. Okay. Yes. So yeah, now I'll do a little bit more detail about how LLMs use so much energy and talk about our sort of holistic and as detailed as possible quantification of energy use, carbon, water use of the sort of family of language models that was developed, of open language models developed at the Allen Institute of AI called OLMO. And yeah, and I'll do that by sort of describing exactly what we measure. So what goes into developing a large language model? I sort of mentioned at a high level, we have sort of self-supervised pre-training on the order of like trillions of tokens of unlabeled data. Self-supervised basically means we're training it. We don't have to actually have human manually annotated data. We're able to get a training signal from just the data as it resides on the internet. This is images, text, Reddit, and code. So those pre-trained models are then supervised, fine-tuned on like supervised manually annotated data by humans that sort of aligns the models with if a human asks a certain question, sort of what we expect as a response. These look like sort of instructions, and this is on the order of like millions of examples. This is really how we get the models to do like the really cool things that they do. And then there's also sort of reinforcement learning, again, from sort of manually annotated human data of, for example, like thumbs up, thumbs down preferences, like this is a better response than this response, and also verifiable rewards. So this is basically like rewarding it for getting the right answer to like a math reasoning question, like a word question. So increasingly, we're like, these things aren't necessarily separate anymore, and we're referring to this as sort of the supervised post-training process. Okay, so if you're interested in the paper, we quantify like a lot more models than the results I'm providing here, and also provide a lot more sort of different metrics and details. But for this talk, I'll summarize it in just sort of like the megawatt hours of energy required to train these different models, and then the sort of corresponding CO2 equivalent emissions years of the average US home. And I'm not going to discuss, if you're interested, I did put it on the slide, so if you're interested, we can talk more about how we're actually sort of calculating and estimating these numbers. But sort of here's the equation that we're using. And I guess the thing to note is that we're including both the operational energy use and emissions, from the actual sort of training in the data center, and we're also sort of trying to estimate the emissions from the manufacturing of the hardware by sort of like amortizing across the expected lifetime of the hardware, according to our data center operators. And all these numbers are based on a lot of conversations with the data center where we actually ran this, trying to talk to the energy provider. They didn't really want to provide us with as many details as we wanted. So this is like a very accurate estimate for this set of models, at least the OLMO models. Okay, so what does this look like? So for training, I guess as you might expect, the emissions increase as a function of model size. Generally, I guess another thing I'll say, these are all like relatively small models compared to like ChatGPT or something like this. We don't actually know how large it is, but it's definitely larger than this. Yeah, but a lot of cool capabilities you get at like the, 13 billion and 7 billion parameter models do lots of really cool things. And I think state-of-the-art models now are like 30 plus billion parameters, like 30 to 70 to maybe 150 billion. So that's sort of the scale. But our 13 billion parameter OLMO 2 model, used about 230 megawatt hours of energy to train, and producing equivalent emissions to about 21 years of the average US home. So we similarly estimate the amount of water that was consumed. You can see maybe the equation looks pretty similar. We can sort of we have a lot of the same estimates or measurements in terms of water. Again, the estimates for the operational use, so what was happening in the data center, I think here are like quite accurate. But for manufacturing, yeah, we are doing our best based on the information that's available, which is extremely sparse. And so we see similar trends here. I guess note that this is typically not reported. I don't know that anyone else who has developed a language model has reported or tried to estimate these things. There is a paper about water use from someone, not at any of the companies developing the models. And so we don't have these numbers for the llama models, but for our Olmo models, the amount of water sort of ranged from about 4 months of the average US person's water use to train that single model to about 7 years and 10 months, maybe almost 8 years. And I guess another thing I want to note is that, I'm providing these sort of like really high level numbers. But something to think about that's really important is that these data centers actually reside in like communities somewhere. And this is mostly, the data centers and the sort of manufacturing. This is typically like potable water from like the local water system that's being used. And similar with energy, like there are actual externalities that are impacting people like where those data centers are located. That's like a lot more than just sort of thinking about this broader sort of US level use. Okay. So that was focused on training. So we also estimated, we have this fantastic model that we've produced. As a reminder, for a given model size, inference energy is going to scale like linearly with a number of tokens. So we also estimate the energy use during inference. And I think probably most people in this room have interacted with a language model. They know what inference looks like. But you have a user who has some query for the model. So these are the sort of the input tokens. The model produces a response. These are the sort of output tokens. I guess the thing that I want to note is that there's typically a lot of sort of hidden computation and hidden tokens that are actually going into this. So in the prompt, you may provide a system prompt, but in addition, there is always a pretty long system prompt that you never see that's sort of instructing the model to behave in the way that a company wants the model to behave. This is in the case of using like an industry, like proprietary model like ChatGPT. In the output, I mentioned these like long chains of reasoning. In some cases, you see them, or you can click a button that allows you to see them. In many cases, you don't see them. So in order to produce the actual response that you see, there's often been this long iterative process of like thinking, planning, refining, and responding. That's what this sort of chain of thought reasoning sort of approach is, where the models are sort of trained to do this sort of long thinking process of like, okay, well, how should I think about this problem? Maybe I want to do this. Ooh, I had an aha moment, which actually happened. The model produces that. Let me like rethink about this, and then it sort of generates the response. And then in practice, this is performed sort of like k times, and then the best response is selected through some kind of like majority vote process, or typically just like another model that was like tuned to basically rank these and identify what's the best response. We didn't actually do any of that in this study. We're working on something right now. But in the production model, this is sort of like what's going into that. So in our study, we didn't actually at the time have any of these models deployed to the real world in a production setting. So we had to sort of simulate it. So we simulated it with a realistic data set called Share GPT, which is a data set of like people's actual sort of queries and responses to a language model, from a language model. And then we simulated it at various request frequencies. So basically the energy efficiency is going to be much better if you're getting as many requests as possible at a given time, which is a realistic setting for a company like OpenAI or Google, because then you can basically maximize your use of the hardware. So that's what sort of infinity request frequency represents. 8 represents basically 8 requests per second, and 1 represents 1 request per second. So it's going to be most efficient use of hardware and least energy use. Least efficient. And then we're reporting kilowatt hours as well as basically the number of inferences that it takes to equal training in terms of energy use. Because I think it's useful to think about, how many like inferences does it take to then start to basically use more energy than was required to do the initial training. I think these trade-offs are interesting and important to think about. Yeah, okay, so this is what these numbers look like. yeah, I mean, I think, so here, actually, the context that's important here, yeah, here's the Sam Altman tweet. So as of, when is this from? Last February, OpenAI was generating about 100 billion words, maybe that means tokens, per day. And so this is also essentially number of tokens. And so you can see that actually pretty easily, at least with these models scales, we can anticipate that the energy use at OpenAI from inference is sort of like vastly exceeding the energy use for training. Yeah, and recall that even in 2022, already at Meta, that energy use for inference was vastly exceeding the energy use for training. And I say this because there's just been a lot of focus on training because it has these like really big high-level numbers. Like I think, if we care about the energy and environmental impacts of AI, we need to be focused on inference, more now than ever. And unfortunately, it's really hard to we really need companies to sort of give us more information about what that looks like. So they don't really report these numbers at all. Yeah, and so towards that goal, yeah, so I've been talking a lot about large language models as it's sort of close to my heart, but also sort of where, I do think it's an exciting technology that is being deployed like sort of throughout everything, the entire economy and our lives, whether we like it or not. But there's many, I mentioned earlier, there's like many different types of AI models, and they have different energy profiles. So with folks at Hugging Face, we developed this AI energy score project. We originally wanted to call it AI Energy Star, and then we were told by the EPA that that is trademarked, and we needed to change the name, so we did, but I will still use their logo legally in my slides. Sorry. Yeah, and so what we did here is, yeah, the goal is that we wanted to provide this sort of like easy to understand rating system similar to Energy Star for sort of understanding the energy efficiency of your AI models. And so to start, we sort of measured the energy use for basically like a typical workload for a lot of different models. And so what a typical workload looks like is different depending on the task. So we looked at text generation, image generation, text classification, image captioning, summarization models. These are all different sort of types of tasks and different families of models or groups of models that you would use for those tasks. And we defined sort of, we used our domain knowledge to try to define what these characteristic workloads might be. We designed them to be hopefully as representative as possible by drawing sort of like example data from like a wide variety of data sets. And then we evaluated sort of I think it was the 100 most popular models on Hugging Face. So these are open source models. This is like the biggest centralized repository of open source machine learning models, or at least it's like the easiest one to use. Yeah, and then so you can sort of see for a given task, like text generation in this case, on the x-axis we have a bunch of different models, and basically how much energy they used on this sort of benchmark that we defined. And then you can sort of see that we give fewer stars to the least efficient models and more stars to the most efficient models. And just some sort of interesting high-level takeaways from this and another study sort of related to this. So generative tasks are more energy and carbon intensive compared to discriminative tasks. So a generative task being like summarization, something where you're just like generating a bunch of text or generating a new image versus, basically just trying to perform a classification. So generating image versus classifying an image or classifying text. Generating something is going to be much more carbon intensive. So if you can get away with actually just doing a classification, that's likely going to be a lot more efficient. We also found that tasks involving images were a lot more energy intensive than tasks involving text alone. And like really importantly, using sort of general purpose models, so using sort of general purpose generative AI models for when you can get away with doing a discriminative task, which has sort of become increasingly popular because the models are so easy to use and they work so well. That is much more energy intensive compared to if there is a task-specific model that you can use for that task, just using that task-specific model. Something that I'm interested in sort of technically is sort of understanding when and how we can sort of identify these task-specific things that we don't have task-specific models for, and then sort of produce a task-specific model for that people can use that is more efficient. Okay. Okay, good. I think I'm actually doing okay on time, which is amazing. Okay, so going back to the language model, this is a paper. All of these sort of OMO energy efficiency results are from a paper that's going to be presented as a spotlight at iClear soon, possibly this month. Okay, so the last, I was talking about the AI model life cycles, right? We talked about training, we talked about inference. We also quantified development, which is another thing that very few, I think no other sort of language model developers have done. And so yeah, typically when you see the sort of carbon emissions or energy use number for a model that is reported, it is what was required to train that single final model that has been released. So like the single Llama 3.1 model, or maybe like the family of like Llama 3.1 models. But in fact, anyone who has developed any AI model knows very well, there is quite a large, that's like the sort of the tip of the iceberg of like the vast amount of computation and work, human work, but also computer work that went into sort of identifying and developing that model. In the case of large language models, we also have to perform hyperparameter search, data mixing. So it's like really important for downstream performance to identify sort of like how much code should you train on versus how many images versus how much text and where that text comes from. And that requires a lot of sort of iteration and ablations. And typically training state-of-the-art models also includes multiple iterations of data generation from the model, selection of that data, training on that data, and then generating more data to train on. Not to mention sort of debugging. So like a bunch of times you're sort of just trying to train these models and they just explode and fail. So there's a bunch of energy that sort of went nowhere. Yeah, in fact, in our paper, I don't have them in the slide, but in the paper, we report the emissions from and energy for training a bunch of models that we never released because they just sort of weren't as good. They went nowhere. Advances happened, and we sort of threw them away. Okay, so the overall, so we can calculate this all in the same way that we calculated the other measures. And then essentially the overall emissions from just the development process, and this is a very lean development process. So at AI2, we have like not a ton of access to compute, at least compared to a large tech company, and just not as many people either sort of running jobs. This resulted in about 98 years of equivalent home energy use emissions and 24 years of water. And I think for us, it ended up being about half of the total energy for training. Because we sort of had to be very, very careful in our energy. There's a lot of human effort and planning that went into, how can we sort of do as little experimentation as possible in order to find like the ideal settings and then run this one long job. Okay, so high-level takeaways. Oh yeah, one last fun result I want to talk about here is so this is a chart from training one of our models of sort of what the actual GPU power looks like throughout training. And you can see that there is these abrupt drops, these abrupt regular drops in energy draw. And Meta also reports that they saw the same pattern in their really large scale training jobs on like entire cluster of like 10,000 plus GPUs. And at that scale, at Meta, it was bad enough that their energy provider for their data center basically had to call them up and say like, whatever you're doing, you need to stop, because they were like rapidly basically pulling and then not pulling so much energy that it was actually causing like detectable changes in the frequency of the energy provider. And then, so as a result, yeah, so this is some code from the PyTorch-based library. So this is sort of how like all of these language models and neural networks are implemented. And there's now this PyTorch no power plant blow up environment variable that can be set when you need to like sort of dampen the energy draw. Anyway, or yeah. And this arose, this is from checkpointing. So this is basically, you have these like 10,000 GPUs, in our case, not 10,000, in our case, 200. But in Meta's case, 10,000 GPUs, sort of all training at once. And then you just save the model. So everything sort of stops, and they all have to synchronize. And then you do a bunch of I/O to save the model to disk. You're not using the GPUs, energy drops. And then you go back to training again for some amount of time. And so like the frequency of checkpointing and the decision, I mean, yeah, whatever. I'm not going to go into detail, but yeah, the frequency of checkpointing seems like a small choice, but at this scale, it actually potentially has like really large impacts. So that's sort of one of the interesting takeaways here. Yeah, another takeaway for me is that transparency is so important. Yeah, so the overall iceberg of development costs. The embodied emissions are also sort of rarely to never reported. There's like one other paper that reported this for an open source model. And then the water use, they're all understudied, underreported, and there's not enough data to really do a good job of reporting it either. And so in my opinion, we need policy to compel data disclosure and the science to inform it, so like what data needs to be disclosed. Yeah, so data center energy use is an insufficient metric. So there's all these different ways in which AI models use energy. And I think, in order to, do a better job of, for example, predicting what that energy use is going to look like in the future, and also sort of optimizing and trying to reduce that energy use, we need much better detail and understanding of what are the drivers of that energy use. Is it inference versus training? And which use cases and applications? Like, is most of this energy use actually from like LLM training and inference, or is it other types of AI models? And then how should that inform where we focus our research and optimization, at least on the machine learning side? Yeah. Okay. So in the case of use cases and applications, this is something I'm really interested in and advocating for. So some people have worked on sort of like life cycle analysis for AI, but I think this is just like so important. So yeah, I think even the sort of AI energy scores are insufficient because I think we need to actually measure, the energy use and ideally be able to sort of tie that to the practical use case applications. I think the work sort of tying AI models to actual like workforce job categories, I think is the closest thing and like the first step towards this. We need to actually tie these energy requirements to the capabilities and the use cases, and then what is the how beneficial is that use case? Like, how much do we need that use case? Is it actually worth the energy? So again, giving a few different examples of AI use cases, right? We have a very wide range. We might be using generative AI to accelerate discovery of, useful materials. We might be using, these are real examples from people who like asked me these questions also. We might be using remote sensing to detect, deforestation or smoke in order to assist in combating forest fires. Or we might be using LLMs to like transcribe and summarize all of your Zoom meetings. Currently, we don't have each of these sort of studies would require like a significant amount of work and expertise and like maybe consulting with me, and I don't have time to do this. Not necessarily me, but right, a lot of expertise is required. But I think we know enough. We sort of have enough data collected now that I think we can do projections. We sort of actually understand if you define, what is the model that you're using, what hardware is it being deployed on, and sort of like what do the data distributions look like. I think we could actually sort of automate, these sort of analyses of all these different use cases, and that would be like really informative because then we can tie this energy use to the actual use or utility in the world. So I've been thinking about how we can sort of empower practitioners who are involved in these AI applications to be able to sort of easily and accurately perform some sort of ideally life cycle analysis of the energy use and environmental impacts of these models, but even on a smaller scale. It doesn't have to be the whole life cycle. It can be just a use phase. how am I doing on time? Oh, I'm over time. Oh, sorry. Okay. That's okay. That was most of what I wanted to talk about. I was going to talk a little bit about Jevons paradox, but that's okay. Yeah, indirect effects are important. Remount effects are important. We have a cool paper about it. You could read it. But yeah, there's many different rebound effects. I'll end on these takeaways from thinking about rebound effects. Characterizing indirect effects is really important. Now I didn't talk about indirect effects, but from the bigger figure, I think how the AI models are actually going to be deployed and used potentially has a much larger impact than the energy use. We need to connect those things and focus on that. I think the other takeaway is that market incentives alone are going to be insufficient to reduce AI energy use. William Stanley Jevons pointed this out in the 1800s with like coal. When we have Jevons paradox named after him when he identified that like efficiency improvements in coal production did not actually reduce overall coal consumption. It actually increased overall coal consumption. We have the same problem with AI now today. It's like not a new problem. Innovation and sustainability are not mutually exclusive. We just need to think about both and try to understand how to connect the two sides, and then we can make decisions based on that sort of like informed measurement. Okay, I'm done. I'm sorry if there's not time for questions, but yeah, thanks.
We do have time for one very quick question. So anybody have one off the bat?
Thanks for the talk. So my question is there a role for distillation or decomposing models into sort of more specific versions? And kind of auxiliary to that is, can we like reduce demand by models just saying, I don't know how to do that, instead of churning?
Yes. Yes, and yes. So I mentioned, exactly. So if you can basically define the task, if you can do a good job defining like what is the task you actually need to do, then like basically distilling like a really large model, or I'm sort of assuming you don't already have like data necessarily for that task, but these large models can be useful for sort of like generating data, and essentially you can like produce a really high quality, smaller, more efficient model through distillation, for example. And I think we totally should be doing that. We don't really have, I think, like the software frameworks that make that really easy, right? And so I think that's the challenge there. It's really easy to just keep using like the LLM API. Yes, and the second part I also 100% agree with. It's something that I've thought about a lot, actually, in terms of like, AI efficiency methodology. So I've thought about this in the context of something I've worked on for like a really long time is sort of figuring out, like you want to align the amount of computation that your model is actually doing to the difficulty of the task. So sort of like adaptive computation. And when you look at models that actually do try to do that, the vast majority of the computation is actually spent when the model is like uncertain. And then so it sort of does all of the computation and then gets the wrong answer anyway, because models are basically not well calibrated and they're not good at knowing when they don't know. And then, there's a separate issue of like the models are actually trained. You may notice that models often are very chatty. Like they just produce really long, verbose sort of explanations and responses by default, and they're trained to do that. And this is another example of where the incentives are maybe misaligned or aligned, where, I mean, you're paying sort of like per token to the company, so they are sort of incentivized actually for the models to produce longer responses by default as well. So that's interesting. But yeah, I don't know if that's like, I 100% agree with you, and I'd love to maybe chat more. Yeah. Thanks.
Well, thank you so much.
Thanks.